Hello, I'm the first author and I would like to introduce our geometric morphometric study affiliated with the Universities of Zurich, Switzerland and Athens, Greece regarding the patterns of covariance between ramus morphology and the rest of the face. The mandible is translated anteriorly and caudal by bone deposition at its posterior border, yet the anterior border is resorptive, which also leads to the elongation of the mandibular corpus. Along with modeling changes at the condylar neck, the mandible grows posteriorly and cranial, but it is translated anteriorly and caudal. According to Enlow's counterpart principle, the modeling process with different amounts of bone deposition and resorption at the posterior and anterior borders of the mandibular ramus not only result in the lengthening of the mandibular corpus, but also lead to increased ramus width, which in turn displaces the mandible anteriorly in a coordinated position with the maxilla. Due to the close connection between mandibular ramus and the position of the mandible in relation to the maxilla, we wanted to investigate the covariation between the shape of the ramus and the rest of the face using geometric morphometrics in adults. We hypothesized that wider rami might be correlated with more prognatic mandibles. To answer our question, we collected lateral cephalometric radiographs of an adult population in order to exclude the effect of growth on our findings. The lateral X-rays had to be of good quality for point identification and position. Patients had to be in habitual occlusion with no documented functional shifts. Of course, we did not include patients with a previous orthodontic treatment or those with craniofacial malformations, systemic diseases, syndromes, or myofunctional disorders. The shapes of ramus and the rest of the face were described with 15 landmarks and 51 semi-landmarks. The landmarks are denoted with squares in the figure, while the semi-landmarks, which were allowed to slide, with circles. The landmarks and semi-landmarks were organized in 5 curves and 2 data sets. Of course, the data collection process was controlled for intra- and inter-rater measurement errors with the procrustis ANOVA and procrustis coordinates for shape and centroid size for size. Finally, the data sets were controlled for outliers using box plots for size and procrustis and squared Mahalanobis distances for shape. We then performed usual geometric morphometric procedures on our data. Information unrelated to shape was removed with a generalized partial least squares procrustis superimposition. The morphological characterization of our sample was consequently provided by a principal component analysis. Sexual dimorphism was assessed both in shape and size. For shape, sexual dimorphism was assessed with the procrustis distance and permutations tests on the mean values of all data sets between males and females. PC plots were additionally visually inspected for signs of separation between sexes in the shape space. For size, the logarithm of centroid size was compared between males and females in all data sets. Furthermore, since the male-to-female ratio of the sample was unbalanced, approximately 1:2 static allometry was expected because males are, on average, larger than females. We assessed the significance of allometry with a multivariate regression analysis with the procrustis coordinates as dependent variables and the logarithm of centroid size as the independent variable. To further control for allometry, new shape variables corrected for the effect of size were obtained for each dataset by exporting the residuals of the respective multivariate regressions. To investigate the covariation between the ramus and the rest of the face, a 2-block partial least square analysis was used. For that, 2 blocks were formed. The first referred to the ramus, denoted with green in the figure, and the second referred to the rest of the face, denoted with blue in the figure. Two separate procrustes fits were applied to evaluate joint changes in shape within the ramus and the rest of the face. The strength of the covariation between the blocks was quantified using the RV coefficient, which can take values between 0 and 1. PLS analyses were carried out with and without the allometric effect. Furthermore, to better control for the potential influence on the outcome due to the unbalanced male-to-female ratio, PLS analyses were repeated with only females. The sample consisted of 159 adult individuals, 104 of them females and 55 males. The mean age of the whole sample was 34.4 years, with no statistically significant age differences between males and females. Intra- and inter-rater measurement errors explained less than 1% of the total shape variance in shape and size. Finally, both for shape and size, no outliers were detected in the sample. With respect to the morphological characterization of the present sample, the first four pieces accounted for 66.1% of the total shape variance of the whole configuration, while the first two pieces for the 45.7% of the total shape variance. The plot of PC1 and PC2 is colored by sex. Yellow dots represent females and blue dots represent males. PC1 depicted shape differences corresponding to skeletal hyperdivergence and decreased facial depth, whereas a hypodivergent skeletal pattern with increased facial depth was evident in the opposite direction. PC2 described the shape differences in the sagittal plane between class 2 and 3 skeletal patterns. Regarding sexual dimorphism in shape, shape differences between males and females were detected in all datasets and were statistically significant, as can be seen in Table 1. Although males and females largely overlapped, some separation hints were evident in the PC plots, like the present plot, where more blue dots representing males are located towards the negative ends of PC2 and PC3. Separate PCAs for males and females were performed to visualize shape changes according to sex. The outline drawings depict only the positive direction of the corresponding PC and sex. The average shape of each group is shown in black, and shape changes are colored in blue for males and yellow for females. Percentage values correspond to shape variability explained by each PC and group. PC1 and PC2 describe the same shape variation in reversed order for males and females and jointly accounted for 54.4% and 42.8% of the total variance in males and females, respectively. Finally, statistically significant size differences between the sexes were also detected for all datasets. Regressions were highly statistically significant for all datasets. However, shape variance explained by allometry only ranged from 2.2% for ramus to 6.0% for the rest of the face. As can be seen in Table 4, the partial least squares analysis produced similar results with regards to the covariation patterns between the ramus and the face for all individuals with and without the allometric effect, as well as females only. Therefore, only results for all individuals with the allometric effect included are presented here. In all individuals with the allometric effect included, 45.5% of the total covariance between the ramus and the rest of the face was explained by PLS1 and 25.5% by PLS2. In the plots, males are denoted with the blue dots, while females with the yellow dots. In the outline drawings, the average outline shape is depicted in black and shape changes in blue. PLS1 on the left described covariance mainly between the width and the height of the ramus, sagittal and vertical positions of the jaws, and thickness of the symphysis. A wider and shorter ramus with an increased posterior curvature in the gonial area was related to a decreased lower anterior facial height, a slightly prognathic mandible with a thicker symphysis, and the prognathic maxilla. On the right, PLS2 depicted covariance pertaining to the position of the lower area of the ramus and changes in the sagittal relationship of the jaws and the inclination of the mandibular plane. A more posteriorly positioned ramus with an increased posterior curvature in the gonial area was related to the class 2 pattern and flatter mandibular plane. Finally, from the findings of the present study, the following conclusions can be drawn for the patterns of covariance between the ramus and face. An increased ramal width correlates with a decreased lower anterior facial height and prognathic mandible and maxilla. A posterior orientation of the ramus in its lower region correlates with a retrognathic mandible and a flat mandibular plane, both of which actually mean that the width, height, and inclination of the ramus are related to facial changes in both the sagittal and vertical planes. I would like to thank you very much for your attention.